Our next speaker is going to be McGinley, who's going to be talking about measurement-induced entanglement and complexity in constant depth 2D circuits.
Thank you, Abhinav. Hi, everyone. So I'm Max McGinley. I'm a postdoctoral fellow at Cambridge, and today I'm going to talk about some work I've done in collaboration with Wenwei Ho in Singapore and Daniel Malz at Copenhagen. Right. So I am a physicist by training, and therefore when I think about computational complexity, my mind typically takes me to problems of simulating many-body dynamics. Now, I've put, as an example, two kinds of models that we can think about that are meant to model processes we find in nature. One of these is atmospheric modeling for weather systems. The other, for example, is the Fermi-Hubbard model meant to model a superconductor. These are both interacting many-body problems, and we can try and make predictions about them using classical computers. And remarkably, in the case of atmospheric dynamics, we can make actual predictions, which invariably come up like this if you live in the UK. In the other case, if you've ever tried to do this, well, we know what happens there. OK, so I'm going to talk about a problem that is circuit sampling. And in a way, I kind of think of this as a form of simulation problem, in that we have some kind of circuit, for example, in the bottom right here, which is some form of many-body dynamics. And we want to somehow mimic that physical process. In particular, we want to generate bit string outcomes with probabilities given according to the Born probabilities that the laws of physics give us. And there's a couple of reasons to think about these kind of problems. I mean, first of all, there's a practical aspect, particularly when we think about geometrically local circuits, that these are basically problems that are set up almost by design to be executable on a quantum computer. But for me, there's also a kind of theoretical appeal, which is that we can relate somehow the complexity or the hardness of simulating this kind of dynamics to the underlying many-body physics of circuits. OK, and in this work, I'm going to particularly talk about constant depth 2D quantum circuits. And I'm going to identify the sort of physical phenomenon of measurement-induced entanglement as being sort of responsible for why these circuits are hard to simulate. This is going to be a theme that will also occur in the next talk, and I very much encourage you to all to stay around for that. OK, so let's just get on the same page. Shallow 2D circuits, I mean, we have a quantum circuit in geometrically local in 2D, made up of some constant number of layers. And because of the constant layer condition, the states generated by these circuits are, in some sense, simple. They have sort of low entanglement. In fact, they're so simple that there exist efficient classical algorithms for approximating expectation values, at least up to some inverse polynomial additive error, due to this work here. Now, despite this, simulating sampling is still hard in the worst case. So that is, if we want to sample from this distribution, that under some plausible complexity theoretic assumptions, that this is hard. And this is in contrast to what happens, for example, in deep 1D circuits, where in essence, we run the circuit for a very long time. We generate a very complicated entangled state, and then estimating expectation values or sampling, they're both hard problems. OK, so why is that physically? Why are these 2D circuits, even in the constant depth regime, hard to sample, even though we have some very sort of strong control on representing those states? So I'd like us to consider what happens when we consider this sampling problem bit by bit. So I can look at the first qubit and look at the distribution of outcomes of bits on that qubit. It will be distributed according to P of S1 here. And that's just some function of the original state psi. Now we can go and try and sample from the second qubit, and we would need to update our wave function psi to some conditional post-measurement state in order to compute that next bit. Now, these first couple of wave functions that I've listed here will be still pretty simple. But the argument is that as one continues this process further and further, the states that one builds up are increasingly entangled and harder to represent classically. This is the phenomenon of measurement-induced entanglement, the idea that when we perform measurements on weakly entangled quantum states, we could actually generate more entanglement, or even longer-ranged entanglement. In the few-body setting, this is very familiar to anyone who's heard of the phenomenon of entanglement swapping, where, for example, one can generate EPR pair photons, measure them in Bell bases, and have, for example, in this case, photons 1 and 6 in an entangled state, despite the fact that they have never physically interacted with one another. And this is going to be a sort of many-body analog of that phenomenon. Perhaps an example, if we think about sampling from the cluster state, which is the resource state for measurement-based quantum computation, when we perform measurements on this state, we know that we effectively execute a unitary circuit in this sort of sideways evolving direction, as illustrated here. And therefore, what we end up with, after, say, measuring all of the qubits in the bulk of a system and maybe leaving some on the edges unmeasured, we end up with a maximally entangled state between two ends of the system, despite the fact that we could have prepared this cluster state in a constant depth circuit. That's something very special about this state. And indeed, those worst-case examples that I mentioned are very much based on MBQC ideas. I'm more interested in what happens generically. So suppose we sort of perturb a little bit away from this limit. If we look at a more generic state, there's no guarantee that when I measure this, that viewing this sort of transfer map in the sideways direction would give us a unitary circuit. So it's not so obvious what happens. But there's been a series of recent works that suggested that there is, in fact, a sort of a robust phase in which this sort of long-range measurement-induced entanglement remains, despite the fact that there is this effective sort of non-unitary dynamics if we think of the system evolving sideways. So just to be specific about what I mean by that, we can say, take, for example, this geometry where we measure all the qubits in region B, leave regions A and C unmeasured, and consider how much entanglement is there between A and C, which are separated by a distance far beyond the sort of light cone distance of this circuit. So the conjecture is that as we tune the depth of this circuit, the depth D, there is some critical depth above which we get long-range measurement-induced entanglement, and below this we get no measurement-induced entanglement. And this critical depth is, again, still order 1. We're still in the constant depth regime. And this has been, let's say, associated with a proposed transition in the simulability of these circuits in terms of simulating sampling from them. So the idea is that once we start generating long-range entanglement, there is no sort of efficient classical ansatz for these post-measurement states, and the algorithms that we have, at least that we know of, will begin to fail. So I'll elaborate on that statement a little later. So this motivates us to think about, well, how does entanglement spread when we start measuring states generated by a constant depth circuit? And so we can think, well, what sort of analytical tools do we have to study this? If we're thinking about random circuits, representing somehow generic circuits, then one might hope for some analytical progress based on similar techniques that have been used to study the dynamics of entanglement in random circuits. There's a problem when we are introducing measurements into the picture, though, and that is that when we perform a measurement, we project the wave function onto some subspace, but we also have to renormalize the state afterwards. And this ratio, this sort of numerator and denominator, make direct computation of any kind of entanglement entropies sort of not possible. So for anyone who's seen these kind of techniques, typically the things we have access to are polynomial functions of the unitaries that go into the circuit. But sort of averaging these kind of things is a lot harder. There is some partial workaround. So I refer to this as a sort of replica approach. I put an asterisk here because this is a little bit more involved than what I say here. But effectively, what happens is that people say, well, suppose that we can ignore any correlations between the state itself and this sort of denominator, this probability. And so we just average these separately. Unfortunately, it's only known rigorously that this is valid if we take circuits on qubits of local dimension q that scales polynomially with the system size. which is not particularly attractive, let's say. So in this work, we sort of circumvent this replica approach using sort of new techniques and get rigorous bounds on measurement-induced entanglement in these circuits. So our main result is as follows. We can define certain natural families of random quantum circuits which have constant depth. They act on qubits of a constant dimension, and we know that on average, the states that come out when we measure on B have entanglement that scale with the linear system size. So we have extensive long-range measurement-induced entanglement, and at the end, I will elaborate on what that says about how hard it is to simulate sampling from these circuits. Good. So how do we actually prove this result? As I mentioned, there's been quite some works using this replica approach, where they try and evaluate entropies, or things that look like entropies, as I should really say. But we go about it in a somewhat different way. So what we do is we actually ask instead an information theoretic question about the entanglement in this circuit. So we have our state phi AC, which is conditional on having obtained a measurement outcome SB. And what we ask is, can we distill Bell pairs from this state using LOCC, local operations and classical communication? Now, we know basically from the very definition of entanglement that if this is true, then our state of interest must be at least as entangled as that Bell pair. And we can think about sort of a family of maximally entangled states here where D prime controls sort of how entangled the state is, or how much entanglement is built in there. The nice thing about this is that we know exactly how entangled this state is. The entanglement is log D. And that, therefore, if we can show that this is possible, we would therefore get a lower bound on the entanglement of this post-measurement state. In practice, what we'll be able to show is that we can't get exactly to a Bell pair, but we can get epsilon close to a Bell pair. And in that case, what we'll have is some sort of small correction, this f of epsilon here. But this gives us a lower bound on the measurement-induced entanglement in this system. OK. This brings us actually to a more info theory or sort of quantum Shannon theory question. And in this regard, we actually wanted to frame this as a kind of canonical Shannon theory task that's known as multi-user entanglement of assistance, which has a very similar flavor here. The idea is we have some multipartite state from which we want to generate bipartite entanglement using LOCC. This is a sort of a long-standing problem. For example, if we're allowed to access many copies of the given state, then there are some asymptotic formulae that are known about how efficiently we can do this. I put this on just to illustrate that this is a sort of well-studied problem in the many-copy case. We, of course, are only thinking about sort of single copy. So what we've really done is basically adapt some methods from quantum Shannon theory in order to study this entanglement of a system problem in a so-called single-shot setting, which also accounts for the spatial locality of correlations in these states. Just very quickly, what we're able to do is to derive an upper bound on this error epsilon, so how close to the Bell state can we get with LOCC, in terms of a statistical mechanics partition function here. So just to unpack this expression, this is a sum over W here, where W is any sort of domain wall that separates A from C. So in other words, we can just think about bipartitions for which each side of the partition is a connected region, and A is on one side and C is on the other. And there are obviously many ways to do this, and this is the bound we get. I put this expression in the very top right corner just for anyone interested. The way we get this is essentially by we're bounding the difference between two quantum states, and the operator inside this norm with which we measure the distance, we essentially decompose into many different components related to these cuts here. And then we apply the sort of triangle inequality, basically, to get this sum over positive variables. This actually bears some resemblance to the asymptotic entanglement of assistance formula, which in this case considers the minimum possible, the minimum entanglement over all possible bipartitions. Here we somehow have a weighted sum of all of them. So that's just sort of for anyone with an info theory interest. But the point is that this is a well-studied statistical mechanics model, at least in the case where this exponent is known. So SAW here is sort of self-avoiding walks, which essentially just describes what are these domain walls here. And so if we can show that the system, this sort of pre-measurement state, exhibits a perimeter law, so in that the entanglement across the cut W scales with the length of W, then this statistical mechanics model orders. It orders at a critical value of beta, which is order 1. And our claim is that when this statistical mechanics model orders, we get long-range measurement-induced entanglement. Okay, so those are the sort of technical parts of my slides. All that's left to say is that our job now is basically to look at a particular circuit architecture and get a lower bound on beta, this sort of coefficient of how much entanglement crosses a cut W in terms of its length. Okay. So for some specific results, some specific circuits, I put this one up first, not necessarily because it's the most natural, but because it's the one we have like the best control over. So in this kind of circuit, it's a two-layer circuit. In the first step, we generate entangled pairs on bonds, and in the next step, we apply random unitaries to all of the qubits that on a given site. And in this case, what we can show is that if we measure this state, we get long-range measurement-induced entanglement if this bond state has has a Renyi entanglement entropy exceeding 2.8 bits. Okay, this is a one-sided bound. Okay, this is not to say that if the state is less entangled, we won't get long-range measurement-induced entanglement. But the important thing is here, we're really working with order 1 qubits and order 1 depth, and we're still able to show this. The same holds if we look at slightly more natural classes of circuits, for example, four local or brickwork circuits here, and we essentially work by keeping the depth fixed and using this sort of qubit dimension as a tuning parameter to say how much entanglement is in this state. Higher Q, the sort of more entanglement we have. These are not particularly favorable bounds, but the key is that there are some order 1 values of Q above which we get long-range MIE. Okay, at the very end, I would just like to connect back to the original question, which is how hard is it to simulate sampling from these circuits? So just to recap why we thought about this measurement-induced entanglement problem, the idea was that as we measure more and more qubits, we generate more and more complex and entangled states. Now, in this work here, which was one of the sort of papers where this simulability transition was proposed, they introduced this very nice sideways evolving block decimation algorithm, which essentially uses a classical ansatz for these conditional states, an MPS ansatz, in order to basically keep track of this process and simulate it in polynomial time. So what we're able to concretely show is that this algorithm cannot work in this high measurement-induced entanglement regime. And I think this is nice that we're able to make some relationship between the physics of what's going on in terms of what physically are these measurements doing to the wave function and the viability of these kind of sequential-based sampling algorithms. So that's a very algorithm-specific statement. Very finally, as we're going to hear about in the next talk, there is some recent work showing that if we have if a certain condition based on measurement-induced entanglement holds, you can show an unconditional separation, complexity theory separation, between that circuit and any sub-logarithmic depth classical circuit. So using our methods, we're able to show that this condition is indeed met for this particular circuit architecture and this particular value of Q. And this gives us unconditional complexity theoretic separation between two analogous classical and quantum resources, in particular constant depth classical versus constant depth quantum circuits. Okay, that brings me to the end. Let me just sort of put up these conclusions. So we talked today about constant depth 2D circuits. I argued that these are hard, not because the state generated by the circuit is particularly complex, but because when we start measuring it, we generate high entanglement and high complexity states. I showed you how we managed to derive some rigorous lower bounds on the measurement-induced entanglement in these constant depth circuits, relating to a Shannon theory problem known as entanglement of assistance. And then we were able to show that at least that there is this phase in which we get genuine long-range measurement-induced entanglement at constant depth with qubits of constant dimension, and related this to various complexity theoretic problems. So thank you very much, and I'll take any questions.
Hello, this was a great talk. In some of your slides, you provide like a lower bound for the QD dimension. My question is, why is that lower bound looks a little bit bad and like has a constant large?
You're right. No, indeed, the quantitative bounds are not great, right? That we don't really want to be working with qubits of dimension 134. The reason is because we've actually mapped in the previous slide here. What we've mapped this to is actually a 2D problem. And in some sense, what we've done is flatten any of the temporal structure of this circuit. Now, in practice, if you work with qubits, the depth, I think, is that this transition is believed to happen is something like 6 or 7. And when you actually sort of remove any of that temporal structure, you get sort of worse and worse bounds. So ideally, what we would like to do is actually be able to map this to a stat-mech problem which, let's say, accounts for temporal structure there. And then I think we'd be able to improve these bounds all the way to q equals 2, as long as the depth was big enough. So that's an unfortunate limitation of our method right now.
Thank you so much.
So I was thinking what happens if you freeze Q to 2?
Yeah.
Then I would imagine, based on your perimeter argument, something special happens at Ly, the depth being equal to Ly. What happens?
The depth, the length of the system size, yeah.
Yeah, the depth and then Ly.
Right. What I've kind of swept under the rug here is that in deriving all of this, what we've had to do is coarse grain the lattice of qubits to the point where, let's say, only nearest neighbor sites are correlated with each other. So for any constant depth, I can do that. I can just group qubits or qdits together into bigger qdits such that we don't have any correlations beyond 2 sites, and then we would do that. So if, let's say, this wouldn't work if we now have a depth that scales with this linear system size, because we would have basically coarse-grained the entire system into one big blob. So that's, again, another...
So do you have a depth, a critical depth, if you fix for just Q equals to 2?
No, unfortunately not. Actually, that's why we need to, let's say, upgrade this so that we can take into account temporal structure. Because actually, at the moment, if we naively do this, what we find actually as we increase the depth, the bounds get worse and worse, which definitely doesn't reflect what's going on. So that's why this needs to be addressed.
Oh, thanks. This is a good talk.
You have time for one more question there?
Yeah. Thanks for the nice talk. And I wanted to ask if the results and conclusions depends on the way you partition ABC.
Yeah, great question. I think largely no. In essence, we can get a bound that corresponds to some stat-mech quantity for any geometry of A, B, C. The question is, does that give you something useful or not? But the statement is that this is a bulk phase transition. This ordering of self-avoiding walks is a bulk phase transition. So I think as long as A and C represent a vanishing fraction of the system, then let's say the physics of this self-avoiding walks is dominated by the behavior in B. So that's really the only limitation.
Okay, let's thanks Max again.
We can build